be greeted. Let's continue with these power series solutions at ordinary points. And the difference in 7.2 and 7.3 is that the recurrence relations and the calculations will get a little bit more messier in this part. But it allows us to deal with more general situations. So I remind you, the situation that we will typically be in is we have the coefficients are polynomials now, not constants, of our second order differential equation. So these are polynomials. This always comes up, I don't know. Polynomials. And the main point is our center, x0, is not a root of the first one. That means that p0, x0 is not equal to 0. And we'll deal with that in the next session, when that would be the case. Okay, so let's start with an example again. I'm just going to do examples. The book puts a lot of formulas and looks awful, but it's way easier if you just look at examples. Okay, so let's look at this. Minus 2y equals 0. It's always homogeneous, right? And we have initial conditions. Oh yeah, so we look at solution with center at -1. So solutions in a solution series in x plus 1. So that means the center x0 is -1, right? You remember that is always how these things work. Okay, so in particular, therefore, our initial conditions should be at -1. So the two initial conditions are minus y minus 1 is 2, and the derivative at -1 is -3. So let's already establish. So our solution will be, we're looking for something like this. X plus 1 to the n, powers in x plus 1 to the n, right? And we know already that this will be a 0 and this will be a 1. And all the rest will follow from these, can be calculated from these two things. Okay. So, well, we start with taking derivatives, right? Oh, this is always the same, but please, on a quiz, always write down all these things. It's a little bit of writing, but I want to see that you know everything that's going on. Okay, now we're just going to plug in. So we have x plus, oh no, sorry, yes. I knew that I was forgetting something. We can plug in, right, in this equation, but the problem is then we want powers of x plus 1, and it's now written basically in powers of x. So we should write each of these polynomials as a polynomial in x plus 1. So this would be, of course, x plus 1 plus 2, right? So let's x plus 1. And the y dot prime. So how do you do this? Remember, the way to do this is you place this x by x plus 1 minus 1, and then expand. So here, if we do this, if we do twice that, 1 plus twice, that would be 2x plus 1 minus 2 plus 1, so it would be minus 1. Okay, so that is plus 2x plus 1 minus 1 times y prime. And then here, I hope that it's clear that it's x plus 1 minus 3y equals 0. This is to make our calculation easier. Okay, and you'll see what I mean with that. So because now we're going to plug in, and so we get x plus 1 plus 2, and I keep my x plus 1 in parentheses, although technically that's not necessary, so that I don't get that I don't accidentally expand. So this is y double prime. Oh, this is y double prime. I'm plugging in y. Okay, so I'm just going to plug in everything now. I'm not going to try to be smart at the moment. I'm just plugging everything in. and then we will figure out what is what. Plus 2x plus 1 minus 1, again keeping my x plus 1 in its parentheses that I don't lose it, n x plus 1 to the power n minus 1 plus x plus 1 minus 3 times a lot of parentheses now because of the way that we organize our stuff. Okay, so that is that, and so this is, I wrote it this way so that I can work it out here. So now I'm going to expand this, but expanding keeping the powers of x plus 1, right? These are all both linear, but there could be also square or even higher powers in general, right? I think the next example might be like that. So what we get? So the first one, if I multiply this with that, the only effect is that this becomes n minus 1, okay? So we get summation n minus 1, n, x plus 1 to the power n minus 1. Now the plus 2, that will give me plus summation 2n, n minus 1 an, x plus 1 to the power n minus 2. The power has not changed. Then the next one, if I substitute this, if I distribute this x plus 1 with this one will make it x to the n, and we have an extra 2 there. So plus summation 2n an, x plus 1 to the power n, and then we have minus summation n an, x plus 1 to the power n minus 1. Okay, and then that's the last one. We do the same thing. We get plus summation an, x plus 1 to the power n plus 1. Now, this is the first time that we hit something like this, that the powers are higher. Instead, before the powers were all lower. So we'll see what effect of that is. So minus 3 times, or perhaps minus summation. Perhaps it's better to take even the minuses, everything inside, all the constants inside, and we don't have to worry about what is going on here. So plus summation minus 3an x plus 1 to the n. Now, so we arrange everything in terms of x to the n. X plus 1 to the n, sorry, x plus 1 to the n. It involves shifting, for several shifting. So here the shifts, I'll do each of these separately. Here the shift would be what? Replace n by n plus 1. Okay. So this would be summation n plus 1. And n plus 1 minus 1 would be just n. And that the index becomes n plus 1. X plus 1, n plus 1 minus 1, that's n. Okay, that's great. And the lower bound we don't have to worry about yet. But there's a be careful. Here, this more general case, we have to be a little bit careful. I'll explain when. What does the shift have to do in the second one? Here, well, here's the shift n plus 2, right? You have to do a shift of 2. So plus summation 2, n plus 2, n plus 2 minus 1 is n plus 1, a n plus 2, x plus 1 to the power n plus 2 minus 2, so n. Obviously, this always has to come out n. The next one, I don't need to shift, so I can just copy it. Oh, I better write it here if I don't want to the space. 2n a n, x plus 1 to the power n. The next one I have to shift again. This will be a shift of n to n plus 1. So this would be summation minus n plus 1, a n plus 1, x plus 1 to the n plus 1 minus 1, obviously n. This is the first time we do this. Well, the first time. This is a different type of shift. Well, here I have to replace n by n minus 1. And so I'm now going to be careful here with my lower bound as well. So remember, the lower bound would be n equals 0 to infinity, right? So if I do this, so the other ones I'm not going to do, but I'm writing this one. So, okay, this becomes now n minus 1 is 0 to infinity. And then a n minus 1, x plus 1 to the power n minus 1 plus n. Okay, that comes out to be n, as should be. And then finally, we get, nothing has to be done there, plus summation minus 3n x plus 1 to the n. So what is the problem now here with this one? Let's look at this index here. If I would rewrite this, is the same as n equals 1, right? So I'm going to be lazy and erase this and write just n equals 1. So the problem is then I cannot combine this with the other ones because there is no zeroed, there's no constant term, right? That's what is missing, right? The constant term. So, and remember, this is all equal to 0. So we have to treat n equals 0 separately. The coefficient of n equals 0 in here. Now I can read this off. So this means that I'm going to put in 0 in all these expressions and see what I get, okay? Because this will be the coefficient of n to the power 0. And the reason that I have to do this separately is because it's not here, right? Because if I put in 0, I get a minus 1, and a minus 1 is not part of my series, right? So what some people do is say, okay, let's put a minus 1 equal to 0, then you have one formula that works for everything. So that is a way out, and it's actually the neater way out, but I think it might be putting you kind of get you confused. So I'm just going to do separately the n equals 0. So what does that mean then? Okay, for n equals 0, the first of these, well, that's just going to be 0, right? The second one is going to give me 2 times 1 times a2, right? n is 0, right? I'm not looking at the powers of x plus 1 because that's just what I choose. The third one, this one again is 0, but this one is not. So I get minus 1a1, right? And don't forget the a's also have to be taken correctly. As I said, in the red one, or the one the penultimate one, there is no such thing, so that's 0 really if you want. And then here we will get minus 3a0. Minus 3a0. Notice that all these numbers should be, there should be a's here, right? They should never be a constant in these cases, but okay. So let's write out what we have here. And this has to be equal to 0, right? Because everything is 0. All these coefficients have to be 0. So this means that 4 times a2 minus a1 minus 3a0 is 0. Now a0 and a1 are the initial conditions. So I should bring them to the other side. So we have 4a2 is equal to a1 plus 3a0. So we see that a2 is equal to a1 plus 3a0 over 4. Notice that to calculate a2, I need both initial conditions. In the previous videos, the solutions, the even ones depended on a0 and the odd ones depended on a1. But here we get this mixture. And so a1 was minus 3 and a0 was 2. So we get minus 3 plus 3 times 2 over 6. So that is 3/6 over 4, 3/4. So a2 is 3/4. What happens then for general n if n is bigger than 0? Well, now I can just copy everything. I don't have to make special cases anymore. So I'm just gonna, of course you could, in principle, you could also put n equals 1, n equals 2, n equals 3, but then you are writing a lot. So let's write everything now up. So what we find is that n plus 1, n, an. So I'm just copying now these coefficients, right? All these coefficients, because they're all plus 2, n plus 2, n plus 1, an plus 2, plus 2n an, minus n plus 1, an plus 1, plus an minus 1, minus 3an. And that always has to be 0. What do we do now with this thing? And this is important. I told you previous time, but that was kind of obvious. Here, we always solve for the highest one. For the highest index. Because what we are using is the principle of recursion. For those who have taken discrete math, you know what recursion is. I'm sure you also know recursion if you have done computer science and so on. Means calculating values from previous calculated values. And therefore, we have to take the one with the highest index because that's the one we don't know yet. And the previous ones we presumably know. So we're going to solve for this one. So 2, n plus 2, n plus 1, an plus 2. And the rest we bring to the other side. Now, notice that there are some like terms that I should perhaps take care of as well. Let's look at what is the coefficient of an here. Well, let's take them in order, perhaps. It's already better to, it's good to organize your thing here because so many stuff to get organized. Let's see. So n plus 2, what's the next one? N plus 1. Okay, let's see what is the coefficient of that. That is minus n plus 1, I'm bringing it to the other side, so it actually becomes a plus. Sorry, yes. an plus 1. Okay, then the ans, there are a few of them. There's this one, there's this one, and there's this one. So if I bring this to the other side, then everything comes with negative sign. So we get, so what is, I write an and then write the coefficient afterwards. So we get, I expand n plus 1 times n. So it's minus n squared minus n. So I expanded this and brought this to the other side, okay? Then we have a minus 2n and a plus 3. Okay, so the blue ones all taken together. That's that. And then what else is there? There's a term involving an minus 1 and then just an minus 1. So you see that it does not just depend on the previous one, but it prevents on the previous, on the one before that, and the one before that, on the previous 3, if you want. Okay, and so we should perhaps solve for this. Let's see, yeah, let's work out this coefficient perhaps. This is minus n squared minus 3n plus 3, and for some reason this is not exactly what they have. What did I do wrong? Did I plug it in with the right coefficients? Sorry. I just want to make sure that I didn't plug in something. 2 10 x minus 1 x plus 1 minus 3. Yeah, I think that is correct. And then because they kind of skip the calculation at some point, so they go a little bit fast at some point. Let's see. 2n plus 2 plus 1, n plus 1 times n, yeah, I have that 2, minus n plus 1, yeah, an plus 1, wait, I think I made a copy error here. Yes, I see already. Yeah, it's so, you have to be so careful, right? You look here. It's much harder on a thing like this that I'm doing. Here, this n plus 1 here, I copied that as an. So it has to be an plus 1. So that was not part of the blue one, and the blue one was this one, right? So these two terms were not correct here, because they don't belong here. They belong to an, which is that's correct. Okay, that's correct, yes. But then, so this one, I have to revise this one here, right? So this one is the incorrect one. So let me write it. Let me do this over. So I'm going to write it an plus 1. So what we have, so this is an an plus 1 now, right? So let me write this a little bit neater here. So this is, the index is an plus 1, okay? And so this is brought to the other side, so it becomes minus n squared minus n. And there is also an a plus 1 that brings to the other side, it becomes n plus 1. So these actually cancel out, I get 1 minus n squared, which is 1 minus n times 1 plus n. Okay? Now I notice that everywhere has a, no, that's not true. No, it's not better. So that's it, now I'm correct. Now I have to solve for an plus 1. an plus 2, sorry. That means I'm gonna, so we have, let's not factor this. That is 1 minus n squared an plus 1 plus 3 minus 2n an plus an minus 1, and this whole thing divided by 2 times n plus 2 times n plus 1. Okay. The book has arranged it slightly different, but the way you arrange this is really not important. And so now, okay, we know already what A2 is. Let's say, as usual, let's make that standard assumption. I want A0 up to A5. Okay, so what should we do now? It is now advised, I would advise now to just work your way up. We know A2, so let's look at A3. So A3. What? This is our recursion formula. Let me color it. So how do you find A3? Well, what should we plug in here? N equals 1. So this is the case n equals 1, right? N equals 1. Okay, so what we get, n equals 1. Okay, the first 1 minus 1 squared, that is 0. Then we have 3 minus 2, that would be just A1, right? I'm plugging 1 in, right? And here I plug in 1, that is A0 plus A0, and divided by, and in the bottom I get a 2 times 3 times 2. Now I know what A1 and A0 are. They are respectively 2 and minus 3. So that is minus 3 and 2 divided by 12. So I get minus 1/12. Let me double check here. No, again, is it, or is it minus 3 and 2, or did I copy that wrong? Minus 3 and 2, okay, that is correct. So there's a sign error here. An minus 1. Did I bring this out to the... Oh, I didn't bring... Jesus. See, even just bringing something to the other side and trying to do too many things at the same time, this should be with a negative sign, right? Because I'm bringing it to the other side. Okay, so this would be a negative sign again. So this would be a negative sign. So this would be a positive here, so we get 5/12. Okay, and what is A4? Well, let's see what A4 is. Now, what would that be? That would be n equals 2, right? Okay, so we get 1 minus 4, that is negative 3. 2, that gives me an A3, right? If I plug in 2 here, okay? Plus, I plug in 2 in the next term, that is 3 minus 4, that is negative 1. A2 minus A1. And all that divided by 2 times 4 times 3. Okay, plugging in equals 2 everywhere. So now you see here that we need not only A1 and A0, but we also need A2 and A3, which we have already calculated. So this would be minus 3 times 5/12. That's the A3. Minus A2, and A2 was 3/4, minus 3/4. And minus A1, that was negative 3 A1, right? So the minus minus becomes plus, yeah? Divided by 24. And now I guess, okay, I think we still have a common denominator here. This cancels and get a 4 here. So I get minus 5/4, minus 3/4. Oh, that is minus 8/4. So this is minus 2 plus 3 over 24. So that is 1 over 24. It comes out slightly nicer here. And again, I'm wrong. What is with me? Oh, I have... Why is my sign different than their sign? I think they also make a mistake because, for one thing, it is wrong. I'm doing the example in the book, but there is a mistake definitely because they write A0 is 2 and then they write in the solution negative 2. So they themselves make mistakes there. So I don't know whether this is now, whether I now make the mistake in my 1 over 24 or not. My 5 over 12, they have a negative sign there, but I think I got the signs correct now, right? Let me see, yes, because they have a negative sign in front, so this, sorry, I just want to make sure that, yes, the formula that I have right up there is correct. And so if I plug in n equals 2, and n equals 1 here, then I get minus, this will give, no. Oh, I see what I did. Okay, no, I made a mistake here. Because I was trying to fix something, I fixed the wrong thing here. This is where I fixed it. Okay, let me do this over again. I'm sorry. The formula is correct, and so let's do this over again because otherwise it's getting too confusing. Sorry, let me fix this here a little bit. Clean up here. Okay. So first of all, let's box our formula again. This is our formula. So we are calculating A3. So this was the case, replace n equals 1. This would give me A3. And n equals 1, the first term disappears. The next term is plus an, so A1, and then minus A0. And in the bottom, I get 2 times 3 times 2. So A1 was negative 3, A0 was 2, and then I get 12. So I get minus 5 over 12. That was the minus sign. A4, now I plug in n equals 2. Okay, so that is minus 3 times A3. I'm plugging in 2, right? So then I get a minus A2 and a minus A1. Okay, and that over 2 times 4 times 3. So that is minus 3 times minus 5, that is 15 twelfths. Minus A2, and A2 was 3/4, minus 3/4. And minus A1, that was 3 divided by 12. So I can simplify this, it becomes 5/4. So I get now 2/4 plus 12/4 over 12. So I get 14 over 48, or if you want, okay, now where do this? Oh, 12. 4 times 3 times 2 is 24. Okay, that is where I'm wrong. So this would be sorry, I'm getting now flustered by this. 96, and I divide by, so the 7 over 48. Okay, that's the number that they also have. And then A5, and I'm going to make mistakes, so I'm not even going to do this anymore. Okay, I want to do a next example where you see how things can even be yet different. So here is another equation, y double prime plus 3xy prime plus 4 plus 2x squared y equals 0. We want to write at the center, we're going to take x0 is 0, so that is nice. That makes, we don't have to deal with these weird powers that get so confusing. So we're looking for a solution of the form a n x to the n, right? And our initial conditions are y0, which is a0, is 2, and y prime 0 is negative 3. Yeah, negative 3. Okay? And so we know that this is going to be a0 and this is going to be a1. All right. Yeah, okay. Perhaps before I go back, I should have said this. So the first example that we were looking at, there was this -1 was an ordinary point because this is not 0. So what is the 0 here is x equals negative 3. And remember, it's the distance between your center and the nearest by root. There's only one, so that's negative 3. That determines your radius of convergence. So here that would be 2, right? This would have this series that I was starting to write down, the first few terms of it. Well, I didn't actually write it down, right? But this series would have radius of convergence at least 2. Now here, notice this is a nicer example. This is a constant here. So this series that I'm going to write down will have, there is no root. That means that the distance is infinite, and this means the series that I will get is everywhere converging. That is nice. That sometimes without knowing the series, you know already in advance that that's what's going to happen. All right, now let's find it. Okay, so we let me write it again here. Summation a n x to the n, y prime is summation n a n x to the n minus 1, and y double prime is summation n times n minus 1 a n x to the n minus 2. And so now we plug everything in, so we get summation n minus 1 a n x to the power n minus 2, that takes y prime, plus 3x. So what is the effect of 3x? If I multiply this, then I get a 3n a n, and that will become x to the n now. Okay, that's already in the right correct power. And then what about this one? Okay, so we have 2, the 4. The 4 will get me summation 4an x to the n. And what would the 2x squared do? So summation 2an x to the n plus 2. Okay, and this is equal to 0. Okay, so we're going to have to do the shifts again to put everything in power x to the n. These two already are, the middle ones are correct, but we still have to work on the outer ones. So here we do the shift n plus 2. Why n plus 2? Because I want to get this to be n. So n plus 2 minus 2, that gives me n, right? So perhaps it's a little bit, you might take, oh, I'm taking this one, I'm going to shift to that. No, make sure that you do the right way, right? And the best thing is to just plug everything in and see that it works out what you're supposed to be work out. So this is n plus 2 now, n plus 1, n plus 2, and then we get x to the power n plus 2 minus 2. So this is exactly x to the n. Okay, plus these two we have already seen they are fine, so I'm just already gonna combine them. And then this one, what do we need to do here? This is a different shift. This is a shift in the opposite direction. Here we have to do n minus 2. And we know that this will affect our bound. So these upper shifts with the plus, they won't affect our bound. We always start from 0, but this one will. So we have to take n minus 2. So this is from n going from 0 to infinity. So now it's n minus 2 from 0 to infinity, which means really n going from 2. Okay? And then we get 2 an minus 2 x to the n minus 2 plus 2, that's axn. Okay. So what does this tell me now? This means that I have to take n equals 0 and n equals 1 separate again, because it is missing here. Okay? So these two, of course, they're all going to be 0, but I have to calculate them. I cannot combine everything. So I can combine only the first 3 for the n equals 0 and n equals 1. So n equals 0, this would be 2 times 1 times a2 plus 0 plus 4, so 4 times a0. And that's it, right? That's the a0. Okay. And this is equal to 0. Notice that from this we can actually calculate a2. So this 2 times a2 is equals minus 4 times a0. So this means that a2 is equal to minus 2 times a0, and that was, if I'm not mistaken, 2, right? Where was it? Yeah, 2. So minus 2, so this is actually negative 4. Okay. N equals 1. So you might think, oh, n equals 0 is going to give me a 0. No. It gives you something, whatever it is that it gives you, that's what you'll be happy with it, right? Okay, so n equals 1. What do we get in n equals 1? We get 3 times 2a3 plus 3 plus 4, that is 7a1, and that's again 0. So from there we can find what a3 is. So we see that 6a3 is minus 7a1, and a1 was negative 3, right? a1 was negative 3. Oh yeah, a1 is negative 3. So this is 21. So we see that a3 is 21 divided by 6, which is 7 halves. We see that I write so far 7 halves, okay, minus 4, okay, so I'm good. So what next? Now we can, for n bigger than 1, we can write down, we can put all the terms together. We get n plus 2 times n plus 1. So this is the coefficient of an plus 2 of x to the n, plus 3n plus 4 an plus 2 times an minus 2, and is equal to 0. Remember, what are we solving for? For the highest index. So we're going to have to solve for that. We get n plus 2 times n plus 1 an plus 2, and bring the other guys to the other side. I'm going to use minus 3n plus 4 an minus 2 times an minus 2, and so we're going to divide this by n plus 2 n plus 1, right? N plus 2 n plus 1, they're gone. And so here we have our general formula, and now we can start plugging in to calculate the next numbers. We have already a1, A2 and A3, right? So A3 and A2. Let's just do A4. So A4, now this means, what should I plug in? 4? No, not 4. Whatever it is, this tells you, oh, okay, if you want A4, then you put n equals 2 in me, right? This is not necessarily always n plus 2. This could be n plus 5 or whatever. Depends really on your differential equation, what is this, okay? So don't assume anything, just see. Okay, so we see this has to be n equals 2, okay? If I plug this in, I get A4 is minus 2 times n plus 4, that is 10, A2, minus 2 times n minus 2 minus n minus 2, and I plug in 2, that gets 0, that minus A0, and in the bottom I get 4 times 3, so that is minus 10 times A2, which was negative 4, minus 2 times A0, which was 2, and that over 12. So we get minus 40, minus 44 over 12, so that is minus 11 over 4. And somehow that's not what it is. Why is this too? Why did I plug in wrong now? 7/2, that's what's correct. So it's this one. A0 was A0 2? Yeah, A0 is 2, and this was negative 3. So I plug in n equals 2, I was saying, right? Let's see what I did here. This is a 6 plus 4, that is a 10. And that was negative 4. Okay, this is 40. Oh, 40. Oh, okay, I see now what the mistake is. Okay. This was stupid, right? This minus is plus. So this 40 minus 4, that is 36 over 12, which is 3. Okay, now I'm there. And then we can also do A5, and if I do it, I'm gonna most likely make a mistake again. So do this very careful. Now, you see these mistakes are so easily made, so try to be careful. Do your calculations, double check your calculations and so on. But I'm not going to subtract too many points if you make mistakes with that. What I really want to see, what is important, and that has to be correct, is that this recursion relation here. And that one, need that, box it, always box it. And I will explicitly say, give me the recursion relation, and then you can find the values from the initial conditions. So I want to recap. This method is exactly the same as before, but there are two things we have to take care of, be careful for. One is that we will sometimes have to shift in the opposite direction, which as a result will lead in this, the result of that, this shift, the result of this shift is that you not always start from 0. And that means that you have to take the values, the smaller values first, separately, because they are not everywhere there, okay? Once you have taken care of that, then you get your recursion relation. So this recursion relation is true for all n bigger than 1, okay? Which is okay, because I was plugging in n equals 2 in this case, right? But it's not true if I plug in n equals 0, because if I plug in n equals 0, for instance, I get an a minus 2, which a minus 2, what is that, right? That's not part of my series. As I said, the solution out is they say, okay, all the a's with negative indices are just 0, and then you have this is a valid equation for all n. But that's a choice you make. Anyways, it doesn't change the calculation. You still have to plug in things. Okay, so this is the only thing you have to be careful of. And then the second thing that you always have to keep in mind is you're going to get an expression that is equal to 0 involving several of these coefficients, and you always solve for the one with highest index. And that is also why we have to really index the coefficients, and that's why we don't write a plus bx plus cx squared and dx, because if you do it that way, you might not realize immediately which one you have to solve for. If you solve for the wrong one, you don't get a recursion relation. Recursion relation means that this index that you have here is the highest index can occur. Namely, all the other guys, all the other a's must have lower indices on the right-hand side. So I would perhaps say it this way. On the right-hand side, on this side, all the indices should be less than this index for it to be a proper recursion. Okay.